about from automorphic Lie algebras to discrete integrable systems.
Thank you. First of all, I would like really to thank organizers for inviting me, and that's not just a general thanks, because I never did any discrete system in my life before, and the program I see, you know, what people doing, and try to find my way to contribute to the field, and the program really inspired me, and a lot of discussions with several people, and the help from, you know, advice from Vasilis, for instance, or from other people were really helpful. The other thing I have to say, because I am a newbie here and just don't know many things, and so I'm not going to do any kind of review. So if things are well known, and many things which I speak will be talking about are very well known, so if I don't make references on original papers, please forgive me. When we will write a paper, we will try to take all, you know, things right, and try to do it's fine with references. And if you advise me at some stage, that will be very helpful in general. So what actually, and also what I'm going to talk about is based on two things. One is just been done last 2 weeks here in the program, because I never worked before with Pavlos and Atidis, and another input you will see is based on our joint work with my graduate student Rhys Berry, and not related to discrete, but you will see how it can be related. So, and the idea of this talk is not to give a short and concrete concrete computation, which I will of course show some results, but rather to explore some philosophy and some view on the subject from outside, because I'm outside of discrete world. How and the basis for that is the experience in continuous integrable systems. So we all know that the origin of discrete integrable systems basically comes they appear as a result of study of continuous integrable systems. So what we have usually Lax representations from Lax representation. We construct Lax representation related to continuous integrable systems. We will discuss Lax representations and in continuous integrable system. Then there is a Darboux transformations, and compatibility of Darboux transformations give us a discrete integrable system. What everything, of course, here well known and for many years. I don't know if every discrete integrable systems come from that scheme, but those which come from that scheme can be really studied in depth, and that's what I'm going to be responsible for. What results we know about Lax representations and continuous integrable systems? First of all, we know a lot of continuous integrable systems. Secondly, we have a classification of integrable systems. So if we take systems of low order or a few equations, or even for one equation of arbitrary high order, we know all systems which are integrable, and we know all Lax representations, and we know the structure of Lax operators. So at least we know for continuous systems we have a very complete picture of integrable systems. We don't have that, as I understand, for discrete systems. We have some classification due to ABS, and but that's not, of course, all. that only, you know, tip of the iceberg. There are plenty of integrable systems hidden. So what I want to do, I want to pass the knowledge from continuous systems through the Darboux transformation to discrete systems. And one of the goal of one of the basic idea of this study is to classify Lax representation. So give a very general description of all possible Lax representation. Why I say all possible? Because for known continuous integrable systems, we know all Lax representations and all cases covered by this picture. So I believe that the most of discrete integrable system, or, you know, discrete integrable systems which can arise from this construction, can be covered in this scheme. To be more, so this talk is about rather philosophy, and if there are some mistakes, not mistakes, misprints, or, you know, some little things, you may forgive me, and if you want, we can show explicit computations later. Let's now talk about Lax operators first, about relations in continuous systems, some very general construction. Of course, everybody who work in integrable equations, they know this construction, but I just fix notations and fix a set of concepts, and then we will proceed, because I need some generic thing. So let's talk about Lax representations. Lax representations. How integrable system can be found, a continuous integrable system can be found. So one way is consider two linear operators, and I will always consider first order operator, because nth order operator can be written as a first order operator. We all know that from linear algebra, so from differential equations. And let's consider two linear differential operators dx plus some u, where u, I will talk first about some matrices, and when at some stage I will link it with Lie algebras. U, which matrix, n by n matrix with entries of u x t, and dt plus v of x and t. And if we act on, and we request that exist a fundamental solution, common fundamental solution of these two linear problems. The solution exists if these two operators commute. So if you can write that ut minus vx plus commutator vu equals 0. So what we have? We have a nonlinear equation. Actually, we have n square nonlinear equations, because n square entries, and but two n square variables. That's underdetermined system. Nonlinear, but trivial, because I can always solve it at once. I can set the general solution of this system is gx, maybe minus gx, gx g minus 1, and v is minus gt g minus 1, where g is any invertible matrix of x and t. That is a general solution, nothing interesting. The situation becomes non-trivial and interesting if, where is the duster? Here. If a spectral parameter is involved, and let's consider, so we need to introduce a spectral parameter. So if you introduce a spectral parameter, for instance, you say dx plus u naught plus lambda a. Lambda is a parameter, is a complex parameter, and the second operator, well, let's actually all theory based on one operator, more or less. Second operator is useful to construct a concrete system, but the hierarchies, all integrable structure is hidden in one, and any of these operator can be taken. So I will take always the first one. Say v naught plus lambda v1, for instance, plus lambda square b. And then if you commute these systems, you receive a polynomial in lambda, and every should be 0, so you will receive a system of equation. You receive polynomial of up to lambda cube. So we have 4 entries, 4 equations, and you have 5 functions, matrix functions. Again, underdetermined. It's underdetermined, but it can be made determined, well determined, because there are gauge transformations. The gauge transformations. And the gauge transformation, that is L, that is A. That is L, L, and that is A, operators. Gauge transformations is the following. So if from L we go to G minus 1 L G, and from A to G minus 1 A G, where G is a determinant of G not 0, and G is arbitrary function of x and t, then the system still compatible, and that is known. What can be done with the gauge transformation? With the gauge transformation, we can fix the freedom here and reduce. We have exactly one function redundant, and we can fix this gauge in a different way. One way we can fix gauge, for instance, we can so-called pole gauge. We can diagonalize matrix A. So G minus 1 A G is a canonical form diagonal. And that is almost, that is a freedom. If we have a diagonal, we still can do gauge transformation, and we can make matrix U naught off diagonal. For instance, if you take operator 2 by 2, on matrices 2 by 2, we have dx. You can always write in the form PQ 0 plus lambda, and here 1 minus 1. Actually, will be some function of x, and this function of x can be by rescaling x removed. So that is redundant degree of freedom. So that is a canonical form of operator with one linear in lambda, and that is fairly general. Fairly general. So there is a gauge, another gauge, and if you start from this L operator, you will receive nonlinear Schrödinger equation. So that is U P T equal Pxx, for instance. If you take lambda square plus 2 P square Q and minus Qt equal Qxx plus 2 Q square P. Or there is another gauge, canonical gauge. In canonical gauge, if you look how that operator transformed, for instance, U naught will be transformed like G minus 1 U naught G plus G minus 1 X plus G minus 1 Gx. So you can choose G and set that to 0. And the operator will be of the form dx plus lambda s. And s square can be equal to 1. And that is a canonical gauge. These two operators, you know, just related by gauge transformation, and the equation will be s t equal s sxx, the Heisenberg model. Equations, and for me, nonlinear Schrödinger and Heisenberg model is basically the same equation, because that is a change of gauge, and change of gauge is nothing but Mura transformation. So if we have Lax pair, we can control Mura transformation. It's just a different choice of gauge. If we fix gauge in a different way, we receive Mura transformation. Of course, if you go further, if you derive this Darboux transformation, discrete system, everything will look different. But because they exist Mura transformation, you can recompute one system to another, and they have absolutely isomorphic properties. And from the distance, if you look from a general point of view, it's the same equation. So I don't want, I want to identify this kind of equations. Why? Now let's talk about Lie algebras and how we can classify equations. Look what we do. We have two linear operators, and what we do, we commute these two linear operators. So we construct LA commutator. That is a compatibility condition of these two linear problems. When we commute that, we commute matrices and we differentiate matrices. And that means we live inside of Lie algebra. So the natural thing to do is to restrict our object not only on matrices but on Lie algebra and consider from the Lie algebraic point of view. And since we're working with finite dimensional objects, it's a finite dimensional Lie algebra, and there is a theorem of Levy and Maltsev that any finite dimensional Lie algebra can be decomposed as a linear space on a semi-simple Lie algebra and solvable radical. And our equation can be, of course, also decomposed on these two parts. And only semi-simple part is nonlinear equation, result in nonlinear equation. Solvable radical will produce in proper basis only linear system. So if we are interested in nonlinear equation, we need semi-simple or even simple Lie algebras. And classification is known due to Cartan. So if we restrict our U, V, A, these entries, these matrices on a simple Lie algebra, that will be a reduced system of a smaller dimension. So as many Lie algebras as we have these systems. But that's not the most general kind of reduction. And what I want to push the agenda, how to classify reductions of the system. We have Lie algebra. Now we have Lie algebra, which entries are here polynomial, but in general rational function of lambda. Now I want to consider a subalgebra of this algebra and reduce system on this subalgebra. If we compute a subalgebra, we have a smaller system. How we can select subalgebra, and in a convenient way, so we can we can develop the spectral theory of these operators and find solutions, everything. The way how to find the subalgebra is the following. So what the object we have? We have algebra Lie algebra, and this Lie algebra over, in general, over field of rational function of spectral parameter. How to find subalgebras? One of the way to find subalgebras, which is useful and actually cover all known cases to me, is the following. We consider automorphism of that structure, group of automorphisms, and we consider some subgroup which is the subgroup of this group, and I will consider only finite. Actually, I will consider infinite later on when we are talking about elliptic case subgroup. And then, if we have a subgroup and of automorphisms, now if we take this A C of lambda invariant elements of this group of automorphism, that will be a subalgebra. That will be subalgebra of this big algebra. And the restriction of this subalgebra will give us a reduction of our system. And all integrable systems that basically people discuss in continuous case can be found in this case. Now let's discuss about, and that leads us to a concept of automorphic Lie algebras. What are automorphic Lie algebras? First of all, let's talk about automorphism of this Lie algebra. Obvious, of course, automorphism is automorphism of algebra itself, and another is automorphism of the field of functions. So we can consider automorphism of algebra, and all automorphisms, the theory of automorphisms of semi-simple Lie algebras is well known. You can find, say, in the book of Jacobson, for instance, complete description of this subject. And these automorphisms basically, well, if applied to SL2, if applied to matrices, if algebra is SL2, these all automorphisms are inner automorphisms. That means we have element A from SL2, A mapped to some G minus 1 a g. That any where g is any invertible, actually any element of SL2 group. What automorphisms of the C of lambda? We are interested in automorphisms which preserve a structure of rational. So if we have rational function, automorphism of the field of rational functions of lambda, and this automorphism can be described as a fractional linear transformation of lambda. So we can say that lambda is send alpha lambda plus beta, gamma lambda plus delta. So what we do with element that is a sigma of lambda. If we have element a of lambda, we send it to g minus 1 a of sigma g. Let's write g f sigma 1 minus 1 of lambda g, and that will be automorphism of this algebra. Not all automorphism of this algebra can be written in this form, but that I'm not going to discuss. Today I will concentrate on that kind of automorphism. There are automorphisms which are not in the direct product or automorphism of this algebra and automorphism of the field. There are, some kind of a very interesting kind of automorphisms. I discussed this automorphism with Victor Katz here, but there is no description of. But this kind of automorphism can appear if we have auto-automorphism. For in-automorphism, it seems to be everything can be written in that form. So what we need, we fix some group, the finite group, and we have two representation of this group, one by sigma of lambda and another by automorphisms of Lie algebra, and then that the action on the element of the algebra. Now we can construct invariant, and that is extension, that is a generalization, a kind of generalization of affine Lie algebras. Because in affine Lie algebras, this automorphism, for instance, how to construct affine SL2. You have Lie algebra which depend on lambda, that is a loop algebra, the product of polynomial of lambda on SL2, and then you construct from for instance SL2 C of say of lambda, you construct the following transformation, and that construction is in the book of Victor Katz. So you consider, for instance, automorphism of algebra like sigma 3 a of minus lambda and a sigma 3, where sigma 3 is the matrix 1 minus 1. And if you consider subalgebra invariant with respect to this automorphism, you receive a smaller algebra which is actually affine SL2. What I want to do, what is the generalization here, that we can consider not only automorphism generated by one generators, but we can consider a non-commutative group which acts on Lie algebra. Non-commutative group. And this non-commutative group will be a group of fractional linear transformation which acts on a complex plane. And the same group will act by automorphism on Lie algebra. And then we consider the invariant objects. Now there is a question: how many? Is it a big object? How many possibilities we have? And the answer is we don't have many possibilities, because if we are talking about finite groups, and the finite groups will be the main subject, that there are only very few cases. And there is a theorem of Klein, Felix Klein, that these cases exhausted by Zn, Zn group, diedral group. It's a regular octagon. You have rotations and reflection. Group of tetraeder, group of octaeder, and group of icosieder. And that's it. That the whole classification of discrete, finite discrete subgroup of group fractional linear transformations. So we have a finite set of possible reductions, and that's what we are doing with Rees, we study these automorphic Lie algebras, their invariance and the automorphic Lie algebras corresponding to all these groups and all possible representation, and that is a finite job. If you, and there is also infinite group, which is in SL2 will be Z2 by Z2 by Z square, and that group is a transformation like that. A of lambda you send to, for instance, can represent by sigma 3 A of lambda plus omega sigma 3, and another automorphism A of lambda sent to sigma 1 A of lambda plus omega set 1 omega 2 sigma 1. So sigma 3 is here, sigma 1 is a matrix Pauli of that. So if you take the elements invariant with respect to that group, you just can take average. Then you arrive to elliptical functions, and you arrive to Lax operators studied by Sklyanin and for Cherednik model, etc. So that will be related to elliptic case. But most of my attention will be to finite group. Now, what results we have for the finite group, and how this result will be passed to discrete systems. Now we have a very good picture of possible reductions and possible automorphic Lie algebras for SL2. That is done. And actually, that was a recent result with Rees, and result is quite amazing. Result is the following: that if so, we have only this possible groups of reductions. So what is the result? The result is the following: there are actually only 4 cases, 4 basic cases to be studied. All this picture can be reduced in SL2 only for 4 cases. So there are basically 4 different reductions of Lax pairs in SL2. If you go for higher algebras, then the automorphism will be involved, and picture will become more complicated, not yet studied, but there are some results. I'm not probably will stop on this result much, but in SL2 there are following results. First, if group GR is a trivial group, then we have nothing but the fix of gauge, and we have generic Lax pair. Second case, if reduction group is Z2, that corresponds to a fine SL2, and I can give example of a fine SL2 Lax pair. For instance, sine Gordon correspond to a fine SL2. Second, if you consider, and actually that is equivalent to GR equals Zn. Any n will do and give the same affine SL2. But that is known result. That is in the book of Katz. If GR is a non-commutative, not non-commutative, is diedral group, Dn, then for any n equal 2, 3, whatever, you will receive a Lie algebra, and I can give a structure constants of this Lie algebra, and that give us another example of reduction group. All other finite groups, so we will receive, I don't know how to say that, ADN, or they will be all isomorphic for every n. They're all isomorphic, and they isomorphic D2, and that is our result with Sarah Lombarda. And what we have shown recently, that if you take any reduction group, tetrahedron, octahedron, and icosahedron, and any representation, they will be all isomorphic to that algebra. So not so many, and this algebra is different from the algebra from the affine Lie algebra. Maybe I should give you explicit formulas. So what we do, explicit formula for diedral group. For instance, you can generate this algebra diedral group by the following three generators. A1 of lambda equal the average over the group lambda multiplied by, and that will be a matrix 1/2 lambda minus 1. A2, you do the same with the matrix. That is, you see this Cartan the generators in the basis of in the basis in the standard basis lambda minus 1, and A3 you take lambda square 1 minus 1, and that is 1/2 lambda square minus lambda minus 2 and 1 minus 1. So that then you can compute commutation relations. You will have infinite dimensional Lie algebra over C, or finite dimensional Lie algebra over automorphic function here will be of this group. There is a function which is invariant with respect to this transformation called automorphic. Is, say, we can write lambda square minus plus lambda minus 2. Obviously, this function, if lambda 2 minus lambda, or lambda 1 over lambda, goes into itself. So over the field C of G, this algebra is finite dimensional over the field of complex numbers is infinite dimensional Lie algebra. So that is example of automorphic Lie algebra. And if you just build L operator, now how L operators related to this algebra, you can write sum of ui multiplied by ai of lambda from I, for instance, from 1 to 3. And then that will be a legitimate L operator. We have only three entries here. One entry, namely 3, can be set to 1 by the same reason as before, by rescaling. And we have eventually we arrive to a system of two equations, a partial differential, which is a result of that reduction. So we have a finite number. We have a complete description of possible reduction of SL2. And the last example, of course, group the reduction group, that one, Z2, Z2, Z square. That give us elliptic L operator, which correspond to Landau-Lifshitz or Cherednik-Chiral field model. Right. And the statement is that there is a variety of equations, and we know complete list of equations, for instance, second order equation on two functions, which all can be obtained from which if you take the second operator like the second operator linear in J, so you have A, and the second operator will be also another term multiplied by J. J will be new spectral parameter. Then actually you can you reproduce a finite list of equations, and the statement is that all known, not known, all integrable equation of second order can be obtained by that construction plus gauge choice, plus Miura transformation. So we, in a sense, we have a complete description of equations which can be obtained by Lax pairs, by 2x2 Lax pairs. Now, if we have a complete list up to Miura transformations of equations, then we can now dream to build a complete list of discrete equations which correspond to 2x2 Lax operators. Of course, that construction works in a high dimension too, and we have examples. Probably later on I will show what will happen with the higher dimensional bigger Lie algebras, bigger than SL2. But we just was working and try to find the discrete equations. So what we have? We have Lax operator based on a Lie algebra which has some symmetry property, which invariant with respect to this kind of transformations. That make implications, of course, on the fundamental solution psi, which now is a function of lambda. Now this trick to find, you cannot take arbitrary g and solve this equation in this way, because if you do, you should be aware that the result is a linear function of lambda. So g must have a special structure in lambda. It's a very rigid construction. Either you can try to find g as a rational function of lambda, which works, and which actually will give us Darboux transformations, or in general case, if you want to solve the initial value problem for these equations, we need to solve some the problem reduced to a Riemann problem, Riemann-Hilbert problem to find a function psi. So what I do now, I would like to develop the line of Darboux transformations. And by Darboux transformations, by Darboux transformation, I mean the following. And that's what we start to do with parallels. So suppose we have L operator. We forget about the second operator, because one operator, as Krzysztof told us, actually define everything. So, and Krzysztof is right. So if we have one operator, L, which depends on our potential, and suppose we have a fundamental solution of the problem. So we have L, which has some potential, in this case, potential P and Q, for instance. And now we suppose to this potential P and Q, for these entries, we have a fundamental solution psi. One thing I forget to say, that all matrices can be viewed as traceless, because trace never contribute. Trace multiplied by unit matrix commute with everything. At a split, system leaves aside. We can ignore it. It's redundant. So all matrices traceless. Because matrix is traceless, you can always that Abel's theorem that determinant of psi is a constant. May depend on lambda, of course, but constant, not depend on x. Now what I want to do, I want to construct new psi tilde, which is m multiplied by psi, such that exists operator L of the same form, so span in the same part of Lie algebra, such that L psi tilde equals 0. If I substitute that here, I will immediately find equation on m, that m plus u psi, now it depends on lambda, of course, m minus m u equals 0. That is a well-known equation. If I assume that matrix M is matrix M, of course, now it's not a pure gauge, depend on x and depend on lambda, and dependence on lambda is rational, or I can even assume polynomial. Why I can assume polynomial? Because I can multiply always on a common denominator, and if I multiply by a common denominator, then situation becomes totally polynomial. So I can assume that matrix M is rational or polynomial in lambda, and that must satisfy that equation. And if I can find this function M, I will find a new fundamental solution, and I will find a new potential. So I will map one potential into another. That calls the Darboux transformation, and that how Darboux transformation can be found, and that everybody knows for centuries, I think. That is one thing. Another thing is, and this M, Now let's look what implication of this symmetry of a Lax operator have on structure of M, of Darboux transformation. So first of all, first observation is nothing to do with the symmetries yet, is that the determinant of M, if it's a rational polynomial, belongs to C of lambda, is a constant, and is a constant because trace of matrix is 0. The determinant is constant, and that will be first integrals of the corresponding Birkeland transformations. Second the symmetries we have will imply the following. I'm talking now only about inner automorphisms that we discussed before. The symmetries tells us if L operator is invariant, L of lambda is invariant with respect to G L sigma of lambda G minus 1, then M of lambda, if you put it here, will be invariant with respect to, so that will be G minus 1 M of lambda is M of sigma of lambda. So if I have to write sigma minus 1. So if I would write that not invariant will map one Darboux transformation into another. So if we have a fundamental solution, psi of lambda, if we have a fundamental solution, and then we do G psi sigma 1 of lambda, that's again fundamental solution of the same system with the same potential. So that impose some constraints on the form of the Darboux transformation. Having this symmetry of Lax operator, we will have a certain constraints, certain symmetry of the Darboux transformation. And these symmetries, maybe I will now show you could you please, where is this person who responds? Could you please lower the screen? What I have to do here? Warming up. So what I can do now, I use this equation for M, and I can find the solution. We can find solution for M, and M here, the Darboux transformation, will be a L operator in discrete system as usual, and as many M as we can find. So many we have L operators, and of course you can ask what can be a power or what can be dependence M of lambda, and there are so-called elementary Darboux transformations, and that is discussed, for instance, in the book of Boris Konopelchenko or many other papers. The elementary and all other Darboux transformations is the result of composition, so we can factorize Darboux in some elementary. What is elementary? It's less possible in lambda, and in the case of nonlinear Schrödinger, that is a very well-known result. So we just use M is a lambda multiplied by some matrix plus M naught. The determinant is M naught is a generic matrix. The determinant is constant. We will find that some relations. So if you substitute, you can find some relations, and you can, in 1-2 steps, you can reconstruct matrix M. For instance, entries F and entries G is just U tilde. It's a new potential, and G is V divided by 2, where V is so tilde is a new operator, correspond to a new operator, transformed potentials, and V the old one. So that is. So if you know U and V, you know completely G, completely the Darboux transformation. That M naught is 1, U tilde divided by 2, V divided by 2, and alpha is arbitrary constant, which you can fix. And actually, alpha tells you where the zeros of this Darboux transformation, or in spectral language where you add eigenvalue for your operator doing this Darboux transformation. And that Darboux, if you substitute, you receive that relations plus Backlund transformation, and you can immediately write a discrete integrable system, just choosing different, and that is well known, and for instance in the book of Boris. But there is another elementary Darboux transformation where lambda stay on the top, and you can construct another system, or you can use, you know, the first operator and second, and to take compatibility, and then you receive, if you take first and second, you receive another discrete dynamical discrete integrable systems. And this Backlund transformation, the continuous equation with one variable, will be nothing but a symmetry of this equation. That is, of course, everything well known with nonlinear Schrödinger equation. If you go to a fine Lie algebra, then the first case, of course, sign Gordon, but we don't take the sign Gordon because everybody knows. We took another Lax operator, which basically correspond to derivative Schrödinger, or to, in continuous case, or to massive Syring model in continuous case. And if you look at this operator up to gauge transformation, up to choice of gauge, you can always bring this transformation in that form. So only two entries exist. And there is a symmetry, and the symmetry is obvious. If you change lambda to minus lambda and conjugate by sigma 1, operator goes into itself. That will immediately impose some constraints on the structure of the Darboux transformation. And because you know this constraint, first of all, should be lambda squared. You should commute. You can immediately find out that the elementary will be with m squared, with lambda squared. In general, if you have lambda squared and have a general ansatz without taking into account the symmetry, the computations will be horribly complicated, and you have a lot of equations which completely messy. But we have this symmetry, we place this symmetry, we use this symmetry, we have a very few entries and a very few steps. We find the Darboux transformation. So all entries A, B, G, H can be found in terms of original potential, and F is a solution of this quadratic equation, and that is the corresponding Backlund transformation. Now you can compute the corresponding discrete system, and that's it. You know, you can compute corresponding discrete system, and that will be system corresponding to affine. The last case, non-elliptic case, is diedral group, and the statement is that in SL2 should be either that operators or operators with this symmetry. And we have not, I anticipate the question that how the ABS classification fit that. I don't know yet, but I bet that every Lax operator in ABS should fit this construction and be a gauge, a Mura transformation, or gauge equivalent to one of those.
You have to put two fields though in ABS.
Two fields. You mean no, I mean that probably backwards you have two fields here, and in ABS you have one.
Yeah, there are systems.
Can be written as one equation.
There are systems of two field system that goes down to ABS.
But goes down means reduction. Yeah. Means reduction, and I think all reductions are here. That we have to check, but that, you know, that is a work in progress, but I think all reductions are here, because from the point of algebra we cannot invent more reductions. We have all reductions are here. The only freedom we have Mura transformations, and Mura is a gauge. So diedral group, interesting example of diedral group, and in diedral group actually the first non-trivial when the L operator have lambda square and lambda minus 2. And if you think now about the Darboux should have operator fourth order in lambda as a polynomial, because otherwise you cannot fit the symmetry and the condition for Darboux. That's a minimum possible elementary Darboux transformation. So what we did, we compute this Darboux transformation, and we compute the corresponding equations, discrete equations which correspond to this Darboux transformation. And here the L operator which emerge in this construction will be fourth order polynomial in lambda if you try to shape it in ABS form, that multiply by everything. Of course, m you can multiply by lambda square, because it's nothing, does not change anything from the point of operator. You can multiply by any constant thing, and by lambda square you can multiply. And so if you look on this operator have three entries, f, p, and q, very specially organized, and mu naught, which multiply by unit matrix. So everything can be expressed in terms of p and q, f, and so if you look on this system, then f, p, and q can be found as a solution of the system of these three equations. Everything can be expressed in terms of p and q, and you receive operator. Actually, the same approach perfectly works for Landau-Lifshitz equation, or Cherednik-Lax operator. What Cherednik-Lax operator is, or Sklyanin for the Landau-Lifshitz. You have dx, and you have this invariant with respect to this group which generate elliptic functions. So wi are elliptic functions of lambda. They can be uniformized, and so this lambda is just some symbol, some variable, whatever. You can all three you can consider as in three-dimensional case, in four-dimensional space, W1, W2, W3, and lambda. You can consider three quadrics, and these quadrics Wj square equal lambda square plus ai, where a are arbitrary constant, and that is elliptic curve. This curve can be uniformized by whatever Weierstrass or functions, or whatever elliptic functions you like. You can be uniformized, and that is there is explicit expression for, and many ways to express it in terms of elliptic functions. Sigma is a sigma matrices Pauli, and f is our field, which is a function of x, and that is a three-dimensional vector of length 1. So if you want to do Darboux transform, you try to find Darboux transform in the same, the Darboux transform, the matrix M should have the same symmetry properties as we described before, and that immediately suggests the elementary Darboux matrix, because that is the minimum possible Darboux matrix you can write. Any other can be factorized on those, and in a very few steps you can determine all the entries of this Darboux matrix. For instance, this matrix sigma y sigma I wi will be multiplied by f plus f shifted in the transformed. Gamma naught is here, gamma is here, so everything explicit. Then you can compute compatibility. Then you can everything explicit here. Then you can write a compatibility for this Darboux transform for different choice of a constant, because here alpha is a constant. When you have a matrix M, the determinant of this matrix should be a constant, and that is arbitrary constant alpha will contribute. So you choose a different alpha different constants, you compute the compatibility, and you have a nice discrete system which transform f from the sides to the shifted one, where coefficients C1, C2, C3 are very explicitly can be written in terms of the same f. So there is and all conditions satisfied. The f square transformed is 1. The length of vector, everything is in explicit form. So everything works in this case. Maybe I will say one thing about Toda operator, and we also did for n wave equation. Toda correspond to Zn reduction. Zn reduction. The transformation is the following. You have L of lambda, then it's transformed to q minus 1 L of omega lambda q, omega minus 1, where q is a matrix of roots of unity, omega, omega square, 1, omega power n equal 1. So if you assume that operator is invariant with respect to that transformation and linear in lambda, that the operator will be exactly for Toda. Actually, this operator is gauge equivalent to nth order scalar operator. And there is explicit formula how to reconstruct. So the Toda operator and nth order scalar operator in Gelfand-Dickey hierarchy is the same thing from my point of view. They are gauge equivalent. It looks different, but they are gauge equivalent. So everything will work. And if you do that with the Toda, you can immediately find that, for instance, if it's linear in lambda, and then you can write that the most general linear in lambda operator is the following: that we have a diagonal matrix phi. Well, phi I put x to integrate later on, and delta is a shift matrix. So delta is a cyclic shift matrix, and that is a general form of operator which has a single pole in lambda and invariant with respect to this group of transformations. So no choice. The sum of phi is 0, and that is a diagonal matrix. If you construct Darboux transformation, you can construct n different Darboux transformations. N different Darboux transformations, and they just all written here, that you have mk, the k Darboux transformation is arbitrary. The matrix AK is a diagonal matrix made from the exponents of this phi, and AK arbitrary constants, all non-zero. So in a if n equals 3, we have three Darboux transformations. If we have arbitrary n, we have n Darboux transformations, n elementary Darboux transformations. Now we can compute compatibility of these Darboux transformations. And if you compute compatibility of, I think, second and third Darboux transformation, you arrive to the following discrete integrable system, where upper index correspond to what? To the field Fi, and lower indices are the shifts. So we have a system of, so n and m goes to we have three discrete systems here, yeah? We have we have three discrete systems, sorry. So we can take any two Darboux transformations, and create a compatibility condition, and we receive three compatible systems of equations, where m, n, and k is on Z3. So we have Z cube, so the three-dimensional lattice, and upper index from 1 to 3. From 1 to 3. Of course, this u is ui is exponent of phi. It's just a logarithmic change of variables. It's exponent of phi. So that is how it works. So all computations very familiar to you, and all things you probably will say you know in one or another way. The statement which I want to push forward, and I bet we will prove it soon, that we will systematically study these reductions. We will have a complete possible set of flux operators. We know this set of flux operators cover all integrable equations in continuous case. That we know already, because we have results of classification. Our results with Shabat, Yemilov, Sokolov, myself, Svinolupov, we were working years to build up the picture for lower orders. There is a global classification of scalar equation in all orders due to Sanders, Wang, and Fritz-Berg's. In all orders, we can answer the question how many integrable equations we have. So, and we know that the Lax pair, which constructed in this way, cover everything known, cover everything which is in these tables. You know, these tables contains finite number of equations. These tables are complete in the sense that all equations which have conservation laws and symmetries and you know, some technical constraints on the form of equation are here in this list, and all these equations covered by that construction of Lax operators. In that sense, this set of Lax operators is complete. And there is a question, and I think that the list is big, but all equations basically there are plenty of Miura transformations which leads from one equation to another. So we have to factorize by Miura transformation, and working with Lax operators and with these invariants, that is a way to look at the problem, you know, from the distance and don't really feel the Miura transformations. So many equations which we look for us as similar, look for us different, but have a similar property, they indeed should be related by Miura transformation. Probably that is a way to give a neat description of integrable equation, not only in the case of partial differential equations, but also in the case of discrete equations. That's what the program which we want to pursue, in a sense. Yeah, I think I finish.
We're running a bit late, so maybe it's best if we save some questions for coffee, and we'll meet at 4:15.